Hi everyone, my name is Rinon, and I'm happy to present to you a project I worked on in collaboration with Amit Bermano, Richard Zhang, and Daniel Cohen-Or. It's got a very long title, so I'm going to go on ahead and highlight the important bit. And that bit is that we're going to talk about learning a part disentangled generative model without supervision. So we want a generative model, and which means that our model is going to take some latent code and produce a point cloud. But we also want it to be part disentangled, which means that we want to have the ability to change, for example, just the armrest on this chair. And we'll do that by splitting our latent code in such a way that each part of the code is going to control a different part of the generated shape. Once we do that, we'll be able to modify just one section of the code and add armrests to our chair. And lastly, we're going to see how to do this without any supervision at the part level. That is, we're going to use just the full ShapeNet object point clouds without using any part level clouds or any segmentation. Okay, so I hope that's clear, but why do we even care about part level control anyway? So beyond the challenge, well, we've seen in the 2D world that disentangled controls really open up a wide range of downstream applications. And in our case, we're really going to see that once we have this part level control, we're going to get the ability to do things like mixing shapes in order to compose new objects using parts from our favorite point clouds. Right? So I think that's pretty cool. And let's see how we can go on ahead and do this. So naively, instead of using a single generator, we could split our model into several different paths, and each of which is going to take its own noise vector as an input. And each of these paths could then create a different part of our chair, right? So for example, maybe the top generator will be responsible for creating the chair back. And let's say we give these generators a way to share some information at the lowest level of the network, so they can coordinate things like the relative positions of the parts, so things don't just break apart or float away. But most of the generative process will be done with no connection to the other branches. Once we do that, we'll gather up all our generated parts and compose the full shape, which is then passed on to the discriminator. The discriminator can then contrast it with their real full point clouds from the training set, and we'll learn how to create our part-based clouds, right? So it's great on paper, but why would this even converge to parts, right? Why wouldn't each generator just learn to create a sparser representation of a full chair? If we add those representations up, we'll still get something that looks like the full chair, and the discriminator will be equally happy, right? So if we want to get a part-based solution, we need to motivate our network to actually learn one. So for a first bit of motivation, well, turns out there's a generative model called the MRGAN that already provides part of what we need. It's a graph-based neural network that generates a tree iteratively, where the leaves of this tree are going to be our point clouds, and they'll basically have 3 features each, which are going to be the XYZ coordinates of each specific point. I won't go into the details of the model, but what you should know is that the graph is built in such a way that points that come from the same branch have a lot of features in common during graph convolutions, and so they tend to have similar properties in the final point cloud. What sort of properties? Well, for example, they tend to cluster in similar locations. It's not really a semantic or part-based clustering, but it's a good start for us. How do we encourage these clusters to be actual parts? Well, we're going to rely on previous works, which show that weak context decompositions of shapes are correlated with semantic decompositions. If we demand that each generator outputs a context cloud, not only will it not be able to cover the entire chair, but will also bias the network into a decomposition that is closer to semantic. Okay? But how do we make these parts context? Well, we train a separate network to predict some auxiliary score that correlates with part convexity. Specifically, we're going to use the average distance of points in the cloud from its context half. Okay? And we'll use this auxiliary network as a loss that looks at each generated part cloud separately and punishes the network when the clouds are non-convex. Okay, so this works, and it does give us some more context decomposition, but there's still a problem. Our representation can still have redundancies. For example, 2 different clouds can just cover the same part of the chair, let's say the seat. Right? the city is convex, so both clouds will be convex. And if the rest of the clouds can cover the rest of the chair, well, the discriminator will still see a full chair cloud and it won't complain. What do? We invent a new kind of loss, which we call the root dropping loss. And suppose we do have a redundancy where two clouds cover the same parts, for example, the cyan and the yellow parts of this airplane. Well, if we throw away all the redundant sign points, well, we still get something that looks like an airplane, right? And the discriminator will generally agree. However, if we throw away the blue points, well, suddenly we have a hole in the middle of our airplane, right? There is no redundancy to cover for us. And if we feed this into the discriminator, it's going to complain pretty loudly. Okay, so we can use the discriminator in order to understand if we have any redundancy or not. And if we do, we can punish the generator accordingly. But there's still one slight problem remaining, and that it's the network we described so far just doesn't converge. Apparently, the task of generating a point cloud where each of the roots can be individually modified just contains too much variation, and the network fails to converge to a solution. So we can overcome this issue by taking a note from Stalgan's mixing ideas. Instead of just training the network with a different input to each generator, we employ different levels of input mixing during training. So for example, we'll occasionally feed only a single latent code for all the roots. And this is a much easier task that allows the network to more easily converge to a meaningful object, right? We'll still need to retain some iterations where we feed a different code into each root in order to prevent the network from assuming that the inputs are correlated, and this way we can retain the disentanglement between the parts. Okay. And so that's it for the architecture and the model. And finally, we get to the part where I can show you what the results look like. And keep in mind that what we're seeing here are not segmentation maps. Right? Basically, the network learned to create these clouds from noise, and we're just coloring each point according to the index of the generator that created it. And if we modify the latent code of one specific generator, only the part that it's responsible for is going to change. So we can change, for example, the back of the chair or the tail of the airplane without changing anything else. Our latent space is still smooth, which means we can do things like interpolations at the part level. And I also promised you this cool additional application. So we can really mix the latent codes from two or more different objects in order to create a new object that shares the properties from the source one. Right? So for example, we can create this airplane, which has the wings from the sample above it and the tail from the sample to the left. And since our supervision was at the full cloud level, our model always generates coherent shapes. If we try to mix tables of different heights, for example, well, the identity of the legs, for example, things like their angle, will be preserved, but the height of the result will be adjusted so that the new table doesn't detach into different parts. And this is actually a profound problem when you try to use models that treat part generation and assembly as two different steps. And because our model does this all in one step, well, it really completely avoids the problem. We also did some quantitative evaluations. Unfortunately, there were no unsupervised disentangled models to compare to. So we compared to both a naive baseline, which we handily beat, as well as some fully supervised ones, which we can still outdo on some metrics, for example, the diversity of generated results. And really, this shouldn't come as a surprise because increased diversity is a property that comes up in many, many previous part-based composition papers. Other than that, we also provide measurements for the level of disentanglement in our model, that is how constrained root editing changes are to a single part. We use several metrics, but the conclusions are the same. The effects of each latent code are largely constrained to one single part. And if you're less fond of tables, I encourage you to look at our supplementary materials where we show visualizations for some of these metrics and some additional ablations. So that's it. And to conclude our talk, basically what we saw is that with good priors like convexity and the tree structure, we can manage to learn part-based models without part-based supervision. And we can also do it in the manner that allows us disentangled control over the parts, which really lets us expand the range of editing and mixing operations that we can apply to our shapes, just like we do in images. Okay, so that's it. Thank you very much for listening. And if you want more details, I encourage you to read our paper or come to our poster session. So thank you very much.